RAS Engineering strives to test the performance of building elements used during construction to provide high-quality results, with the belief that testing and discovering energy-efficient solutions with fast payback is not only possible, but makes financial and economic sense.
Here we have the testing equipment set up on the windows. The blower is connected to the air chamber by flexible ductwork. The chamber is attached to the wall using the clamps for a tight seal. The green tube is a sensor that measures the differential pressure in between the environment and the interior air in the chamber. We will be using a blower to pressurize both windows one at a time. This is the interior side of the window. As you can see, the top window has the backup window installed, while the bottom window is just a standard window. We are setting the pressure gauge at 50 pascals to test the upper window with the backup window installed. This screen comes from the computer showing the results of the airflow and pressure. The program automatically calculates the annual cooling cost for this window. Now we will disassemble the chamber and reassemble it to pressurize the lower chamber covering the standard window below. We will set the pressure gauge for the same pressure we used on the upper chamber and turn it on. You can see again the ductwork is expanding as more airflow is passing through. The difference is an extra 300 CFM passing through the bottom window into the interior of the room. This airflow was blocked by the backup window on the first test. Here on the screen we see the results of the testing. The annual infiltration is almost 902 air changes per hour, and the estimated cost of air leakage is $37 per year in cooling alone for a small window of this size. And of course, the cost of wasted cooling air and energy will rise on windows of an even larger size. We start by installing the two temperature sensors, one on the glass and one on the frame of the upper window with the backup window installed. The same is installed on the standard window below. We are now preparing the chamber, which will act as an equalizing chamber for both windows. We will apply heat into the chamber by using a heater. At this time, we will install the heat flux sensor on the top window. This sensor is going to measure the heat that is passing through the glass in watts per hour per square foot. This will help us find the resistant value of the assembly or the conductance. Now we're installing the heat flux sensor on the interior side of the wall. As you can see, we have two heat flux sensors installed, one on the front of the wall and one in the back. We are now applying heat. In order to calibrate the sensors and get accurate results, we are measuring the interior temperature with a portable temperature meter. This is a screenshot from the computer connected to the sensors. It gives us the temperature from both sides of the wall represented by T1 and T2, as well as the heat flux and the U, which is the conductance of the assembly in between the exterior and the interior. After finishing the testing on the upper window, we remove the equalization chamber and install the same sensors on the bottom window of the exterior side before reassembling the equalization chamber. Now we are installing the sensors on the interior side of the lower window. Same procedure as before. Now we are applying the heat and monitoring the temperature to make sure we have the same value as the previous test. Finally, we get the results from the computer. complete with the temperature for the exterior and interior, as well as the heat flux and U value. This is the exterior part of the window mock-up showing the chambers attached to the exterior. We will run smoke into each chamber and pressurize it. Then we will go to the other side of the mock-up wall and measure the particles that pass through each of the windows. The top chamber has the standard window shielded by the backup window, and the lower chamber has the standard window alone. We will test the standard window now. The fog machine produces smoke which is dragged through the ductwork using a fan. As you can see, the smoke is coming through the window, which is an example of poor caulking and sealing on this standard window. As the air with the smoke is passing through the chamber, we are going to measure the particles that are leaking through the standard window. We are going to compare the measurements we are taking on the standard window with the results from the backup window. Now we will repeat the same test on the backup window. We will use the same amount of smoke and test the particles that leak through. Finally, we remove the air chamber to show the remaining smoke that could not pass through the complex path created by the extra sealants.